All right. All right, so we're finishing up chapter 7 today. What was chapter 7 about? It started out actually with, if you look in the book, E1 and E2 is actually in chapter 7. But it's better for me to explain E1, E2, and SN1, SN2 all at the same time, because they are competing reactions, but you can store them one way or the other, depending on what you use. Strong base, good nucleophile, change the solvent. So that's why I did that. So now we're going to finish up chapter 7, which is basically stability of alkenes, naming alkenes, E and Z, and alkynes, right? And so we started with alkynes on how to make them. We figured out we can make them with either geminal or vicinal dihalides if we use a very strong base, like T-butoxide and or sodium amide. But then we also figured out that we can use sodium amide to remove the proton and turn it into a nucleophile, okay? Now, the problem with this here is it works best with primary alkyl halides because it acts as a nucleophile. But in secondary and tertiary substances, it acts as a base. So it does E2 reactions. Okay. So we have to compare and contrast that. We need to make sure whenever we're using an acetylide ion, we're using a primary alkyl halide. All right, questions on that? Okay, so what other reactions do we have to get alkenes? So to make alkenes, we did a dehydrohalogenation to make a double bond, or we made a dehydration to make a double bond, right? And we said that those double bonds are more reactive than sigma bonds, okay? So what can we do? Well, let's do one of the simpler reactions. We can take our alkene here and turn it back into an alkane. Seems like a long way to go, but if you only have alkenes and you want an alkane, you can do this. And so because this pi bond is more active than the sigma bonds, we can do what we call catalytic hydrogenation, meaning we are going to add hydrogen across that double bond, okay? Now, we have to use a catalyst because hydrogen, like a carbon-carbon bond, is a nonpolar bond. We have to activate that bond, right? And so we're going to activate it with a metal catalyst, okay? When we do that, we're going to be able to add one hydrogen on one carbon, one hydrogen on the other carbon. Don't know which one goes where because we really can't tell, okay? So when we look at this in a kind of a regioselective reaction, we have what we call a syn addition, meaning both hydrogens are going to have the same side of the double bond. Remember, your double bond here is trigonoplanar, right? So it has two flat things and it's flat all the way across, all of those. Okay, and so it's going to add across one side of the double bond. Okay, so instead of having it add to the top and the bottom, which we call anti-addition, this is what we call syn addition. Okay, so we can see that really well when we use these cyclohexanes. Remember, we like to demonstrate the cyclohexanes so you don't have to worry about the stereochemistry or rotation. Okay, so if we look at the double bond here and we did our hydrogenation, we could not tell whether it was syn addition or anti-addition. We can't tell if they're adding on the same side or on opposite sides, but we can tell when we restrict the rotation with the cyclohexene right here. In the cyclohexene, we see that the two hydrogens are added to the exact same side of the ring, and that proves we have syn addition. Okay, so how does that work? Okay, well, we have to activate that hydrogen bond. That hydrogen bond is nonpolar. So what we do is we take an active metal surface and we have the hydrogen come and sit on the surface. And instead of being bonded to hydrogen now, it bonds itself to the metal. So we have a hydrogen metal bond. That hydrogen metal bond is now activated, but it's on the surface of a solid. Okay, so what we have to do is we have to have our alkene come down and sit on the surface of that solid. Now notice that, again, we're trigonoplanar here. This is all one flat plane. And so the pi cloud is the one that's coming down to touch the surface. When it does that, these activated hydrogens can then add across one of those. And when it does that, it means it's losing positive charge on the other, and it'll add another hydrogen with its electrons to the other side. But it's going to be on the same side of the alkene. It's just carbon 1 and carbon 2. Okay, so that's why it's a syn addition. It has to add that way. All right, so questions on that? Okay, so the rate associated with the catalytic hydrogenation has everything to do with sterics. If you only have hydrogens, you can fit that alkene closer to the metal surface, right? Because they're small. As you add one methyl group, you know, that methyl group is probably going to stick up a little bit and it'll still be able to react. Two methyl groups, it gets a little harder, but by the time you get to 4 methyl groups here, it's hardest to react because it can't sit flat on that surface. So it is the slowest of those to react. And it's all about sterics. It has nothing to do with electronics. Okay. Oh, wait, maybe it does. Isn't a more substituted alkene more stable? So now we have two things. We have sterics and electronics. In fact, most reactions that you'll go on for are all about sterics and electronics, which is why I'm bringing it now. So this is more reactive for 2 reasons, because it's less substituted and it can get float closer on the surface. Less reactive can fit further away from the surface. We have lower reactivity. Okay, does that look like something you can imagine in your head? All right, so we can do that same thing with any number of double bonds. Okay, so your alkene only has 1 double bond, but your alkyne has 2 double bonds, right? So if we have catalytic hydrogenation and you hit the first double bond, what's your product? You go from 2 pi bonds down to 1 pi bond, which makes it a alkene, right? Doesn't catalytic hydrogenation also reduce down alkenes? Yeah. So can you stop at the alkene with catalytic hydrogenation? No, it's going to do the first one, then it's going to do the second one, and all you get is your alkane. Okay, so the same catalytic hydrogenation that reduces alkenes to alkynes will reduce alkenes to alkanes, will also reduce alkynes to alkanes. But what if you wanted to stop at the alkene? You know, the alkenes are kind of useful. We can do stuff with them, which we'll find out next chapter. So we have to poison our catalyst or make the catalyst less reactive. Okay. So in our normal stuff where we use palladium or platinum or nickel as our catalyst here, all those are going to be reacted enough to do any double bond. So if we take that and we poison our catalyst, and we call that a Lindlar's catalyst, and I'll talk about that in the next slide, or we can use this nickel borate, which is also a less active catalyst, we can stop at the alkene. But what kind of addition are we going to get? Are we going to have our alkene is going to be a specific isomer? It's going to be the cis isomer because we're doing both hydrogens on the same side of the alkyne. Okay, so we always end up with both hydrogens on the same side of the alkene, giving us a cis isomer. Okay, think about it with your in this case here. If we're having, instead of this come down, you have an alkyne, the one side that's going to touch that metal surface is going to add both hydrogens to the same side, giving you the cis alkene. Okay, so that being said, what if you don't want the cis alkene? What about the alkyne, the cis, the trans alkene? If you want the trans alkene, you have to use a different catalyst system. You have to use a different system. In fact, this isn't even a catalytic system. This is what we call the dissolving metal system. But let's talk about this right here, the Lindlar's catalyst or poison catalyst and the cis addition. Syn addition to give us the cis alkene. Okay. So by poisoning the catalyst, we're going to put another metal there that makes it less reactive. Okay. So most of the time we add something like calcium carbonate with lead. Lead and quinoline quinoline is an organic molecule with nitrogen in it. And what that's going to do is that's going to say, okay, no longer is that hydrogen bond that hydrogen bonded to the metal is going to be as reactive because some of it's going to be to lead, which is a less reactive, and therefore it's going to lower its selectivity. However, it'll still only add sin because we're at the solid surface of the catalyst. Here, because we've added the boron, it takes the reactivity of the nickel down again, and we only get that sin addition, and we end up with a cis alkene. So each time we do either one of these catalysts, and Linlar is, if you see the word Linlar, say cis alkene. Linlar, cis alkene. Nickel boride, cis alkene. And then you just kind of figure out what the R groups are about where the alkyne was. Okay. So I said if you wanted the other isomer, you have to change the chemistry. Because all this chemistry happens at the surface of a solid, we can only get syn addition. So let's change the mechanism. Okay. This is kind of a weird mechanism for us to do. We haven't really started with this kind of thing yet. We're going to do radical chemistry in chapter 10. But this is an introduction to single electron chemistry. Okay. So in the case of the alkyne, if we want the trans alkene, we need to do it stepwise. And we do it with when we do a metal like sodium or lithium in its metallic form. So it has one electron in its outer shell, either one, sodium or lithium. Okay. And it wants to lose that electron to become a +1 metal ion. Okay. So we're going to do this in the presence of ammonia, which is a liquid at -30°C, but that's where our hydrogens are coming from. Not only that, it can support the ions and the radicals we're going to be forming. So the first step in the reaction is that we're going to take this lithium. It has one electron in its outer shell. It's going to give that electron to the alkyne. And when it does that, notice we're doing one electron. That's a single barbed arrow. Single barbed arrow means one electron, right? Now the one electron comes here, but notice the two electrons that were on the alkyne carbon here are going to go and be on the other carbon. So that means two electrons have transferred to the other carbon. I didn't even write that up there. That's great. Anyway, so what you're ending up with is you've changed hybridization from sp to sp2. And in this orbital of your sp2 hybridized orbital, you have one electron. And in this sp2 hybridized orbital, you have two electrons. But notice you still have your p's, your unhybridized p's making your double bond. Okay, so we're only taking one of those double bonds away and we're changing our hybridization. So now we have this is now an anion. It's a Lewis base. It is a nucleophile. And so it's going to abstract the hydrogen from the nitrogen that's here. And it's going to give us a vinylic radical. Okay. So the vinylic radical means you have a vinyl group or a double bond with a radical actually on the sp2 hybridized carbon. So now we have one electron here, we still have more metal around. That lithium's just throwing its electrons away, and we end up with another anion. We now have another Lewis base. We can now abstract another proton, and we end up here. But notice that for stability, our radical anion here is in the trans configuration. Our two orbitals with electrons in it are in the trans configuration. Those two orbitals are the ones that are going to accept hydrogens. Therefore, we're going to get the trans hydrogenation in the trans alkene. Does that mechanism make sense? It's a little different than what we've done before, but we're transferring one electron, and then we're getting two different functional groups, including a nucleophile. And they're opposite each other, so they're trans, which gives us our product. And then we're going to get another electron, making another nucleophile and transfer one more protein. So this is technically a Bronsted-Lowry base, because it's accepting the protein.
Would you need 2 molecules of lithium?
Yes, required. 2 molecules are required, or the reaction stops out.
Yes.
Good point. So if, and actually it should stay on there. Good point. Let me put 2 equivalents of sodium. Okay. So, all right. So then Actually, I'm going to do retrosynthesis the next chapter. So I'm going to stop there. So that's the end of chapter 7. Okay. So what I'd like to do now is I'd like to start my review, and then we're going to talk about reaction tables, which is the activity for today. All right. Questions on that? All right. I'm going to go ahead and pull up my review. It's not done. It will be done in about an hour. Go download it off of the Canvas site. Let me show you what the other one looked like, actually. Before I started doing this, let me stop sharing and pull up this one. So this is what my review looked like before. Oh, let me share. Sorry. Share screen with that one. Yeah. Share. All right. Okay. So this is what it looked like before I decided to make it a little more elaborate. What I would do is I would go through and talk through all the different points on what is on this table here and say, you know, this is what I mean, this is what I mean, this is what I mean. But I decided to get elaborate. And so that's why we're going to show the one on the iPad. So I'm going to stop sharing. And I hope you appreciate that it's going to be a little more exciting. And iPad.
Are you sure the Word document too still?
Yes, the Word document's already on there. In fact, there's one for chapters 1 through 4, 5 through 7, and 8 through 11. So those are already published on Canvas under resources. Okay, so that's that list of must knows. Okay, then there's some stuff I'm going to throw in that's really good to know, but must knows or get you to the 75% line, please. Okay, so this is my new review, and I actually I teach another class. Actually, I taught 2 other organic classes where I had other books and they had better graphics. So I started stealing graphics from them. So you'll see some different graphics and maybe a different image that'll lock in your head a little bit better. So in chapter 5, this is the exact same statement from that list there. These are all the different things that are on that other list there. And we're going to go from, kind of individual by individual point right here. So the first thing we got to do is look at our RNS. Okay. And of course, we're going to follow. Oops, let me move this over a little bit. There we go. Still sharing? Okay. Yeah. So we have those 4 rules for prioritization. Atomic number, if you can't define that, see what's attached to it. If you have double bonds or triple bonds, you count those each time. And if you have isotopes, the higher weight. Okay. Then once you've assigned your priority and you have your lowest priority group behind you, you go for, if it's clockwise in priority, 1, 2, 3, it's R. And if it's counterclockwise, it's S. Okay. Practice that again. You have that practice sheet you can download. Actually, I'll make sure that I have the keys up here soon too. Okay. So the next thing I want to talk about is projections. I know we did Newman projections in the last chapter, but this is also a very powerful tool for our next chapter because we get to see where things are. So you got to make sure you understand the difference between your stereo projection here and a correct Fisher projection. Notice this Fisher projection is wrong. The one that's marked out. Why is it wrong? The OH is on the top. All the carbon, the longest carbon chain must be in the vertical axis. That's a requirement for your Fisher projection. Longest carbon chain in your vertical axis. If you do not convert this, you cannot tell whether it is an enantiomer or a meso compound or what. You have to convert it to this, the correct structure. That's why I wanted to make sure that I identified what a correct structure was and a not correct structure was. And then, of course, our Newman projections and the different types we have. We have the anti-staggered, we have the eclipse, we have the staggered gauche. And then we also have the fully eclipsed, but that's not on here. Okay, so know these projections because we get to use them for our mechanisms. We get to use them to make stereochemistry. We get to use them to make the correct isomers in our regiochemistry and alkenes. Then we need to make sure we remember our isomers here. If they're constitutional isomers, don't worry about it. If they're stereoisomers, we have 2 kinds. We have the stereoisomers for alkenes, EZ, cis and trans. But then we also have the optical stereoisomers which are the ones with 4 different things bonded to carbon, chiral carbons. Okay, and if you only have 2 of, if you have a non-superimposable mirror image, you have a pair of enantiomers. Enantiomers always come in pairs. If you have more than one stereocenter, then you have diastereomers. Okay, so let me define a little bit more about that. Enantiomers, non-superimposable, always come in pairs, must have 4 different groups. And if it doesn't have 4 different groups, it's an achiral molecule. Okay, so what about diastereomers? Diastereomers have 2 or more chiral centers, making 2 to the n possible isomers. Okay, that means there's always 3 or more. How can we get 3? You have a pair of enantiomers and a meso compound. That's 3 isomers. So you always have at least 3 or more. In fact, you can have 3 stereocenters and still only have 3 isomers, because the 4 isomers, because the other sets cancel each other out as meso compounds. So remember that enantiomers always come in pairs. Meso compounds have a mirror plane, and the set of these is diastereomers. So right there. And then we want to make sure we remember that rotation of light. The only way we can tell the difference between one isomer and the other is the rotation of light. Okay, so one isomer is going to rotate light equal and opposite to the other isomer, and we call that specific rotation. We take into account the temperature, the length, the concentration, and the observed rotation. And then if you have a mixture, but it's not 50-50, then we have what we call enantiomeric excess. And so you have some optical activity, but for every one you have rotating in that correct direction, you have one canceling some of it out. So that's how you get to the optical enantiomeric excess. Now, what if you have equal amounts of one and the other? What's that called? Right, it's a racemic mixture. So a racemic mixture has no optical activity. Achiral compounds have no optical activity. Meso compounds have no optical activity. Only chiral centers have optical activity. All right, so that brings us to chapter 6. Now, technically in the book, chapter 6 was just FN1 and SN2, but I included E1 and E2 because I wanted to compare and contrast the mechanisms. So I'm going to go through this first and then hit the second one second. But so the first thing we got to make sure we understand with our chapter 6 is the degrees. We have to go back to chapter 2 and say, well, oh, what are degrees? Degrees of carbon are based on how many carbons are attached to it. But the degrees on halides are what kind of carbon is that halide attached to? And so we add methyl halide. Technically, you can have methyl in carbon if it's only a methane. Okay, so we have the methyl group here. And it's different because it's not technically a primary because it only has hydrogens bonded to it. So make sure we know that it's bonded to a methyl group, primary, secondary, tertiary, and what the general structures look like, because it tells us something about reactivity. Okay. And then you need to be able to define nucleophile and its different types and effects. By effects, I mean nucleophile versus base. Okay, basicity, type and effects. Strong base, weak base, big base, small base. Small base can act as a nucleophile. Big base can't act as a nucleophile. You know, think Megan Trainor there. You know. Anyway, anybody get that? All right. Leaving group. What's a good leaving group? What's a bad leaving group? I don't sing, so I'm not going to do it. Anyway, all right. Solvent effects, types and effects, and then substrate types and effects. So let's look at nucleophile. This is a different chart than you've seen because I love this chart better. I love this chart more. I'm better at English. No, anyway, I would say. So these are our good ones. Okay, they all have negative charges. They're all oxygen and sulfur or halogens. Okay, technically, chlorine and fluorine are moderate nucleophiles because they're not as acidic, which means they're weaker bases. But then we have oxygens with delocalization, neutrals. Neutral sulfur and neutral nitrogen are actually moderately good nucleophiles. And then we get to our poor nucleophiles. Notice they are all oxygen and they are all neutral. So, and they're all protic. These are all in that poor group. They're all protic solvents, they're all poor nucleophiles. Okay, and number one thing, a nucleophile is equal to a Lewis base. Not a Bronsted base, a Lewis base. Basicity. Basicity is a thermodynamic effect. Can you steal a proton away? Nucleophilicity is a kinetic effect. Can you make a sigma bond? Okay, so we have trends right here. With increasing size, we have decreasing basicity, increasing nucleophilicity in aprotic solvent, but the opposite in the protic solvent. Okay, so make sure we know those trends. Okay, this is the same chart. These are leaving group effects. Again, the weaker the base they are, the better the leaving group. Look at the pKa's. These are the conjugate acids. These are strong conjugate acids making them super weak bases. These are very weak acids making very strong bases. Makes them poor leaving groups because as soon as they leave, they'll want to react. Okay, solvent effects. Know your protic and aprotic solvents. Ooh, I'm not gonna move that one. So the protic ones are, and we can have some nitrogen with hydrogens on there. I just don't have any here. Oh, actually we did. We did ammonia. In that last chapter, ammonia was a protic solvent. It actually transferred a proton. That's where we got our hydrogen. I'll put that on there. And then we have our aprotics here, where we have no acidic protons. No hydrogen bondable protons. Then we have to have substrate effects. We got to know that in each of these mechanisms, whether or not a primary, secondary, or tertiary is favored in the reaction. So in the case of SN2 reaction, because we have to have both things at the same time, and sterics is a factor, methyl and primary are faster. But in the case of trying to lose something to form a break a bond to form a stable ion, we know that the secondaries and tertiaries are more stable, so they're faster. So know your substrate effects. And this is just SN1 and SN2, and there's the same kind of trend with E1 and E2. All right. Then the next thing it said was know your coordinate diagrams, your mechanism, and your rate law. Okay. So in our SN1, we have a two-step mechanism, including an intermediate, which makes our rate law first order. So 2 humps, first order. 1 hump, everything happened all at the same time, one concerted thing, which means both concentrations are important, meaning we have a second order rate equation. Okay, so that's what I mean by rate, order, rate equation, and reaction coordinate diagram and mechanism. Okay, now that leads to the next topic, which was carbocation stability. The more substituted, the more stable, and it's because of both inductive effect and hyperconjugation effect. These keep adding together to make the tertiary even more stable. What's more stable than a tertiary carbocation? The allylic and the benzylic. Those are even more stable because they have conjugation working for them. All right, so let's talk about rearrangements. We can only do 1,2 rearrangements, okay? And we have 3 types. We have the 1,2 hydride shift, has to be the 1 and 2 carbon. We have a 1,2 methyl shift, has to be the 1 and 2 carbon. And we have a ring expansion for 3, 4, and 5 membered rings. 3, 4, and 5 membered rings. They don't do it for 6 because they're in a ring string. Okay, so then we have compare and contrast. When we look at an SN1 reaction, think tertiary substrate because you've got to form a carbocation. Think poor nucleophile because otherwise it would react. Think protic solvent because it has to support the cation and the anion. Now, for an SN2 reaction, think smaller substrate. You want to have as little sterics as possible. A strong Lewis base. You can speed the reaction up by adding concentration because both components are important. Protic solvents are preferred to make sure the charge is not supported. So it makes it more nucleophilic. When the charge is not supported, it is more nucleophilic. And then, of course, our leading group kind of is the same no matter what. Bigger, more polarizable, the less basic, the better the leading group. Okay, now let's again go to solvent effects again. Nucleophilicity increases down the column with ion size. That is the opposite of basicity in a polar protic solvent because the cation and anion are more supported. Meaning that in polar protic solvents, we have the anions and the big fluffy ones, the big fluffier anions are better nucleophiles than the smaller, more diffuse anions. Okay. Now, in polar aprotic solvent, it parallels basicity because it doesn't support the anion very well, and therefore basicity and nucleophilicity are congruent, and fluorine becomes the better nucleophile because it has a smaller point charge and it's not supported than chlorine, than bromine, than iodine. So the halogens reverse order with solvent. Make sure you write that down. That the halogens reverse order. Iodine is more nucleophilic in protic solvents. Fluorine is more nucleophilic in aprotic solvents. Getting that trend down, because how am I going to ask that question? I'll probably have two questions, one back to back, saying iodine, iodine, solvent acetone, solvent methanol. Which one are you going to pick? Anyway, so that's how that question would be really asked. So, and then of course we have our compare and contrast here. This is all the different things we talked about, but we want to add benzylic and allylics. We talked about that a little more in our next chapter, chapter 7, when we were talking about elimination reactions, specifically the Zaitsev caveat. Okay. All right. So then the last thing we're going to talk about here, and this is a different table than what you have in yours, but it's the same thing, is that all the different functional groups you can make based on all the different nucleophiles you can use. Okay. So we have all these nice strong nucleophiles that are going to make all these different functional groups. We have some neutral ones that as soon as they lose a proton, they can become neutral organic molecules. But they are in there stepwise. All right, questions about chapter 6. Because we're going to move on to chapter, then there's the compare and contrast. This should actually be at the very end. I'll move it. Now, technically, chapter 7 is the E1 and E2 and reactions of alkenes and alkynes, which we just finished today. So these are the different rules that are on the just written sheet. And I'm starting to fill out these right now. So E and Z works when you have more than 2 substituents. You prioritize one carbon of the double bond. You one thing attached to one carbon of the double bond. You prioritize the things attached to the other carbon of the double bond. If they're on the same side, Z, opposite sides, E. Okay, stability trend. More substituted, more stable. And why? Same thing with the carbocation. Hyperconjugation and inductive donation. The same 2 reasons for carbocations make the stability for alkenes. All right, so then let's look at the different reactions, their rate laws, and their reaction diagrams. Okay, so when we're talking about our E2 mechanism, it's a second order because your base has to pull the proton off as those electrons are ticking down as the leading group leaves. So it's a one-step concerted reaction, meaning that tertiaries are better than secondaries, better than primaries. favored by a strong base and favored by polar aprotic solvents. How do you remember that? Well, I'm not forming a carbocation, therefore I want a polar aprotic solvent. If I want to form a carbocation, you need a polar protic solvent because you want to support that cation. Remember that if you're making a cation, polar protic. We're not making a cation, polar aprotic. Okay, we have one step in our reaction. This is a different picture than you've seen. But again, our rate order depends on the concentration of the base, concentration of the substrate. Just like an SN2 reaction, vary each one independently, it'll double, vary them both, increase them both, and it will quadruple. All right, which leads me to the SN2, E1. E1 is a first order kinetics because we create our intermediate. Our intermediate is a carbocation, which means polar protic solvent, okay? Tertiaries are still faster than secondaries, which are faster than primaries. But the difference here is we want a weak base. Remember, basicity is about an equilibrium. And so if you have a strong base, it's going to shift the equilibrium over more quickly. A weak base, it's going to take more time. You can form that carbocation, and then you can have that happen. What's the problem with carbocations? They'll rearrange. Always look for rearrangement. Every time you form a carbocation, look for rearrangement. Okay, and then regiochemistry. Both E1 and E2 have regiochemistry. When possible, you're going to try to form the more stable product, and we have names for those. Those are Zaitsev rule. If everything is okay, you're going to form the more stable isomer, okay? You're going to form the more stable isomer and the more substituted alkene. However, if you have resonance, you're going to form the more stable isomer, which is the one that has resonance. They're going to be in conjugation. So it's not really breaking the rule, it's defining the rule if you already have an alkene. Then we have the Hoffman rule. If your base is too big and cannot reach into a secondary, it will take one from a primary and give you the least substituted or a di-substituted alkene. That's the Hoffman rule. Okay. All right, let me go see what else we have on our list here. Oh, that's going to be here. Okay, so that's regiochemistry. What are beta hydrogens? Well, the alpha carbon is the one with the halogen on it, or the water on, or the OH on it. The beta carbon is one carbon. And you have to look at all of them to figure out which one's going to give you the most stable alkene. Okay, when does that not work? When you have it locked in a ring. You have to have your leading group and your hydrogen anti-periplanar to each other. So identifying beta hydrogens and having anti-periplanar beta hydrogens are required. So make sure we look for that as well. Dehydrohalogenation versus dehydration. One removes acid, one removes water. Overall, the mechanisms are very similar, except that they're not. Right? One is base mediated, meaning you use an entire equivalent of base to take that acid off. So one is base, which is the dehydrohalogenation. And one is acid catalyzed, because you want to protonate the alcohol. So no, they're not the same reaction. They're completely different mechanisms, but they accomplish the same thing. They have the same regiochemistry. They have the same selective chemistry or selective chemistry. You're still looking for an anti-periplanar system when you're looking at your E2 eliminations in either one of those. Okay, but one is base mediated, one entire equivalent of base is required. One drop of acid is required. Okay, hydration and heats of hydration. So the hydration and heats of hydration just tells us that how we really know the more substituted one is more stable. Okay, and we looked at that in comparison with like when we were the different kinds of catalysts we have to hydrogenate our alkenes and our alkynes, right? So if we think about our metal catalyzed hydrogenation, they're the more substituted is more stable, therefore it's going to react slower. The less substituted, the more reactive, the faster. Now, that also goes to the heats of hydrogenation with the catalyst system we use. If our catalyst is too strong, we will not stop at an alkene going from an alkyne. But if we poison our catalyst, knock down the reactivity just a little bit, we'll get that to happen. But in both cases of poison catalyst and non-poison catalyst, metal catalyzed hydrogenation is syn addition. Your alkene has to sit on a surface. But what if you want a transalkene? Transalkene, you're going to change the reaction. You're going to dissolve two equivalents of sodium or lithium in there, transferring one electron, forming a radical anion, which acts as a base and takes a hydrogen. Then you're going to form another anion. It's going to act as a base. And it gives us a trans configuration because the intermediate, the alkene that we're forming, is going to be trans because it's more stable than the cis. Okay. The different Zaitsev rules and caveats. Then we have the total compare and contrast of E1, E2, SN1, SN2. And that's this thing right here. Make sure you talk yourself through this. Hey, this is T-butoxide. Why does it say it can do an SN2 reaction? Well, that's a methyl group. There are no beta hydrogens. That's the only reaction it can do. It cannot do any elimination reactions. But I told you if it's a big bulky base, it's always going to do E2. Every other substrate, E2. Talk yourself through this table. Talking yourself through this table. Okay? An unhindered primary can do a SN2 reaction. So what if I said you have a methoxide and ethyl iodide, and you ran the reaction in acetone at 5 degrees? Okay. Then I said you had the exact same reagents, but you ran the reaction at 80 degrees. What's going to happen at the 5 degrees? Lower temperatures favor substitution. Higher temperatures favor elimination. So, well, SN2 is favored here. You can, if you heat it up, have a good base, act as a base, and form the elimination product. Okay, but everything else has to do an E2. It can't act as a nucleophile. Can't get in there. It's too hindered. It's got to pull on a beta hydrogen. All of these do substitution reactions because they're good nucleophiles. They're weak bases, good nucleophiles. But your tertiary can't do that. It has to form the carbocation. And no reaction, no reaction, no reaction. It's not good enough to, if you can't form that carbocation, it's not. That's how to talk your way through this table. So then you ask yourself a series of 5 questions. What is the substrate? Primary, secondary, tertiary. Is it a good nucleophile? Is it a poor base? Is it a good base? Is it a big base? So is it a good nucleophile or a bad nucleophile? Is it a big base? Is it a little base? What solvent am I in? What's the temperature? So you can take any of those combinations and talk yourself through this table. I have a primary alkyl halide. I have cyanide ion, and I have it in acetone. No, let's put it in water. Okay, I have a good nucleophile. I have a primary alkyl halide. Does it matter that it's in water? Primary alkyl halide can't form a carbocation. It's going to be SN2. All right, let's do something else. I have isopropyl bromide. So we have the bromine on a secondary carbon. We're going to react it with methoxide. And we're going to do it in methanol at 80 degrees. Secondary. it can still do SN2. Methoxide, it's a good nucleophile, but it's a better base. And we're heating it up. So what's it going to do? Elimination. Ask yourself the questions. Those questions in that order. I'll put it in the review. Okay. So if you ask yourself those questions, when you can look at any set of substrates, you're going to say, write it down. Secondary, good nucleophile, solvent, temperature. It must do this. Okay. It's not confusing. You just have to use like a flow chart. Make your own little flow chart for the questions you're asking and what they're going to give you. Okay. Questions on that? Okay. So let's see what else we have. Zates of rule, compare and contrast. So yeah, I'm going to move that slide down to the last one. So that is chapter 7. So I will be doing RNS again on this test because I want to do 5 through 7 because I have to use stereochemistry anyway. I will be doing all the projections, even though Newman projection was technically before, but we used it in chapter 7. So I'm going to use all those projections. And so I will upload this in about an hour, maybe an hour and a half, with all the things in there, including the 5 questions to ask yourself. And I'll probably also slap on there the 5 things that can happen in the mechanism up in chapter 6. Okay, so when you are using these, I want you to go back to your homework and ask those questions. Even if I got it wrong last time, then we're going to get it right this time because I'm asking the questions in the right order. Okay. And then you can talk yourself through this, and it's not a mystery. It's a process. You just get comfortable with the process, and that takes practice. All right. Any questions on the review? Okay, now we're going to go to something a little different. The last thing that I want you to do here, and let me go ahead and find it. Okay, no, it's probably on here. Oh, I don't already have Canvas up. Okay. Oh, okay, good. All right, if we go under resources, took me like 3 days to figure out how to do a button on here so that you could just do it directly with resources. But once I got it, I got it. So we have our patterns of mechanisms. We have something that's not published yet. We have reaction table. Okay. So on reaction table, that's the next thing we're going to do. Okay. So we have at our disposal about 11 reactions or 12 reactions, right? Okay. So the reactions we need to include would be like catalytic hydrogenation, dehydrohalogenation. SN1 is one whole, that covers everything. SN1. So you need to do SN1, SN2, E1, E2, dehydrohalogenation, dehydration, catalytic hydrogenation of an alkene, catalytic hydrogenation of an alkyne, poisoned hydrogenation of an alkyne, and dissolving metal of the alkyne. The only other reaction we introduced in the alkanes chapter, but we're actually going to redo that in chapter 10. So don't worry about the radical hydrogenation. I'm sorry, the radical halogenation of an alkane. Don't worry about that on this table yet. We're going to get to that later. But that is in chapter 4. That was that. Remember, alkanes only do 2 things: they burn and they do radical halogenation. So, but we're going to do that in chapter 10 because I want to show you the methods. Okay. So go through there. Now, the other thing to do is to, if you look in your book, let me pull up the book. Documents. If you look in your book, and I'm going to share this now. Zoom, share screen. Right here. If we go to chapter let's start with chapter 5. I don't know where I got this copy of the book, by the way. Let's see, why does it matter? At the end of the chapter, after the homework, there's a table here. And what it does is it goes through every concept in this chapter. Okay, so it goes through, can I rotate this? Rotate. Okay, yay. And so let's blow it up again. There's a concept map in your book. There we go. And so it goes through isomers, what we're talking about, stereoisomers, chiral centers, what the requirements for each of these things are. So this is kind of good for a concepts to getting here, but it doesn't really help us with the reactions. But if we go to chapter 6, why does it matter? Okay, stop. Where is it? Okay, where is it? Come on. There we go. If you look at the end of chapter 6, there's this one here. It gives a summary of the SN2, SN1 mechanisms, everything I've just given you as well. And it gives you all the functional groups you can do. But what's really cool is it does it for chapter 7 as well. Chapter 7. And so what you really want to do is at the end of each chapter, we want to look at this, because it's going to basically sum up in a visual sense what's happening at the end of each chapter. And there's a good table on this one. There we go. Rotate 90 degrees, blow up. So it goes through the mechanism of everything. It talks about whether it's hindered or whether it's not. It goes through all the different combinations, anti-coperiplanar, bimolecular weight stuff. This is a different tool. If you don't like the way I laid it out, they have it laid out a little differently. And so that you might like that better. And then looking forward, when we get to chapter 8, which is what I love about these end of the things is, okay, let's go counterclockwise there. One more. Oh, it's upside down now. There it is. Rotate counterclockwise 90 degrees. And then, oh. Okay, well, it's upside down, but you get the idea. When we get to here, it's going to show you the mechanisms. And these are the transition states of all the different mechanisms. I love this because if you can imagine what the transition state looks like, you'll know the stereochemistry, you'll know the reactions, you'll know the products, you'll know everything. And so I'm going to draw your attention to this when we get to chapter 8 as well. All right, questions on the next exam? This is page 389. But again, this is the next chapter. So don't worry about it just yet. But you can worry about it when we start it on Monday. Okay. All right. So there are going to be 40 questions on the exam. Mostly multiple choice, but there's going to be some drawing, okay? You're going to draw a Newman projection of an intermediate, maybe. We're going to have to draw some, Fisher projections. We're going to have to look for mirror planes. We're definitely going to be doing a lot of SN1, SN2, E1, E2. I'm going to ask you questions about the mechanisms. I'm going to give you reactants and products and enough information to make what you're going to form as your major product. Now, remember, when we talked about major products in SN1 and SN2, we really didn't talk about it that much. But at E1, E2, we have a difference. We can all have major product and minor product based on the base we use, okay? Because we have so many different beta hydrogens, we're not going to do 100% one thing, but we're going to do a major product based on the rules we have. Zaitsev rule, Zaitsev caveat, Hoffman. You should be able to pick out the major isomer. Now, I might say on a drawing question, draw the major and minor. So please read the question twice. Okay. And the rest of the time is yours to ask me questions. Okay, I have stopped sharing. Okay. Or you can go start studying, or I can go finish this and put it online. But the reason to do the reaction table before this exam is it shows you the different things. Oh, I forgot to show you something about that. I'm sorry. It's under here. Let me share my screen again. I'm sorry, I forgot. Google Files. It should be that. Okay, so here's the best way to do our reaction table. Okay, you're going to do all those different reactions I talked about that are in chapters. There is no reaction in chapter 5 technically, but in the case of SN2, we have stereo and regiochemistry, right? We're going to show inversion of stereocenter. That goes in this table here. So we're going to do something like this is an addition reaction. We're going to add something across a double bond. We require water and an acid catalyst. It gives you what kind of regiochemistry. We're going to do this more. Like for your alkenes, when we're forming alkenes, we're going to form regiochemistry as more substituted, less substituted. So here we're going to have elimination reactions, substitution reactions. SN1 is going to be its own thing. You're going to have a general starting material as an alkyl halide. And you're going to put here secondary or tertiary. Because SN1 reactions require secondary or tertiary. Requirement, polar protic solvent. Right? Requirement is polar protic solvent. General product is going to be a substitution product that is mixed. We have mixed stereochemistry. It's going to be half R, half S, because it formed that carbocation, top and bottom. Basic mechanism, substitution with carbocation, substitution without carbocation. Whatever it takes to get that kind of in your head. Other, carbocation can rearrange. And then the chapter it's going to go in. Because when we add all the reactions for, in fact, this is in chapter 8. This isn't in chapter 8. So, but we're going to see these, we're going to do elimination reactions here, substitution reactions here. So you're going to have SN1, SN2, SN, E1, E2, plus catalytic hydrogenation, poison catalytic hydrogenation, dissolving metal reduction, dehydrohalogenation, and dehydration. All of those are going to be in here. So we have elimination reactions, and then we have, which are the dehydrohalogenation, E1, E2, and then the elimination reaction is the dehydration, acid catalyzed, base mediated, etc. Questions on how to fill this out? I feel this is a very good way to do it. The other thing to do is to, and I will start doing this when I start doing this one, is put a, add color to this, like put both of these as blue and then this is red, because these are the two carbons that were already on your substrate. And the red thing is the thing that changed. Oh, we have to add a red hydrogen too, because that had it because of that. So if you color code it, so say what was added, it'll become immediately obvious to you of what happened. Okay, so I will actually update this to include color coding as well. All right. All right, sorry, I got it too excited about the chart. All right. And so this is one thing, you fill it out, again, it's only those few things, upload it tonight as part of your study plan. And tomorrow, go ahead and if you have questions, I'll be in my office. You can email me tomorrow morning. If you have questions, or you can email tonight too. I'll answer email till about 8. That's when I'm gonna bottle wine, so. Probably want to email me after that. All right, thank you very much. See you all tomorrow. Bye.